Welcome to ServoSoft, the optimal solution. This tutorial explores the Kinetic Buffer feature, including what is a kinetic buffer and its primary objective, and understanding the differences between normal and backup power modes. Please note that Kinetic Buffer is available in the Pro version. What is a kinetic buffer? A kinetic buffer is used to store energy mechanically in a rotating disc, also known as a flywheel. Both terms, kinetic buffer and flywheel, will be used interchangeably throughout this tutorial. The kinetic buffer's objective is to supply power to the DC bus in the event of a main supply power failure to keep the system running and bring it to a controlled stop. During a mains power loss, the kinetic buffer can also be used to absorb energy in a rapid braking event. The first step in using the kinetic buffer feature is to understand the three operating modes: normal, max stop, and backup power. Normal mode is the standard sequence for long-run continuous operation. While normal mode can be used to define any sequence, there are specific scenarios that are best handled by max stop mode and backup power mode. Max stop mode is focused on rated max stop values, where, for example, gearboxes have 2 times T2 max to bring the machine to standstill and does not consider the continuous thermal conditions. Backup power mode considers the loss of main supply power starting at a certain time in the sequence for a duration. And it is exactly this scenario, the loss of main supply, that the kinetic buffer is used. Let's begin with this one-axis project with a large inertia load and a normal sequence of 6 sinusoidal moves repeating every 30 seconds. Next, I'll add a second axis, a rotary mechanism, and then enable the kinetic buffer feature in the rotary mechanism form. When the kinetic buffer is enabled, most rotary mechanism inputs are disabled except for the inertia values, and these kinetic buffer specific inputs are enabled. These inputs define almost everything about the kinetic buffer. Constant velocity is the critical value, which combined with the inertia values specify the amount of kinetic energy stored in the flywheel. Maximum velocity is the upper limit on how fast the flywheel can rotate. Or put it another way, this is an upper limit on the amount of energy the flywheel will hold. Minimum velocity is the lower velocity design value. While the flywheel can drop to 0, the minimum velocity value is an operating speed below which there is little energy left in the flywheel. This can also be thought of as a safety margin. If the velocity drops below the minimum value or equals or exceeds the maximum value, then a warning message in system check is displayed. The next two variables are the DC bus upper and lower limits. When the DC bus rises to the upper voltage limit, the kinetic buffer engages and the drive accelerates the flywheel to feed energy from the DC bus to the flywheel as needed to maintain the DC bus upper voltage limit. The flywheel speed increases as more energy is added, up to the max velocity limit. One design object is to size the kinetic buffer, so the max velocity is never reached. If reached, an alarm occurs in system checked. Of course, this is only relevant if there is a lot of stored energy in the machine when the power loss occurs. When the DC bus decreases to the lower voltage limit, the kinetic buffer engages, and the drive decelerates the flywheel to feed energy from the flywheel to the DC bus as needed to maintain the lower voltage limit. This is done until the flywheel reaches 0 velocity, which is not desirable. If 0 velocity is reached, an alarm occurs in system check. When sizing a kinetic buffer to meet the needs of an application, it comes down to these variables and the flywheel inertia. Let's start with the most important question. How does one choose the flywheel inertia and constant velocity? Well, the first question is if this is a backup supply or generating application. Usually, the kinetic buffer acts as a backup supply application. Fundamentally, this is an energy problem. So how much energy do we need to feed the DC bus? Recall that energy is proportional to the inertia and velocity squared per the formula. While there are losses in the drive's inverter, this basic formula defines the sizing criteria. Deciding the constant velocity is really an iterative process, adjusting both the inertia and constant velocity with regards to the application needs. However, typically 2500 to 3000 RPM is common. The important point is a kinetic buffer works better at higher velocities, where a small change in velocity at, say, 3000 RPM results in a larger amount of energy than, say, the same velocity change at 1000 RPM. This also makes the flywheel less dynamic, with lower deceleration rates, using less motor current, and therefore lower motor winding losses. Ultimately, this is more efficient in getting energy out of the flywheel and into the DC bus. Finally, lower deceleration rates also makes the flywheel easier to control. When the kinetic buffer feature is enabled, the axis sequence is locked down and cannot be changed in the sequence form as it is defined by the constant velocity in normal mode. The only time the kinetic buffer velocity changes is in backup power mode during the loss of main supply power, as the kinetic buffer reacts to the application requirements to maintain the DC bus voltage within the lower and upper limits. When in max stop mode, the kinetic buffer maintains its constant velocity. The kinetic buffer is assumed to be in its own protected cage and always runs at its set speed until a power loss triggers it to be used for backup power management. In master-follower applications, when in normal operating mode, the kinetic buffer axis maintains its constant velocity regardless of any changes to the master. So that's all the background. Let's size the kinetic buffer for this application. The objective is to size the flywheel inertia, motor, and drive such that it can feed enough power to the DC bus to meet the backup power sequence and bring the machine to a stop in one 30-second move. This is achieved by defining the following. First, backup power sequence including the time of power loss and duration is defined, and then specify the kinetic buffer variables to meet the requirements. The very first value we need is the amount of energy in the rest of the system. From the kinetic buffer axis form, I'll open the power versus time chart, which has an extra plot just for the kinetic buffer. And here you see we need to deal with about 123 kilojoules. This is all the energy in all axes in the power group, excluding the kinetic buffer axis. I'll start with 1000, 3000, and 3100 RPM for the speed values, and say 10 kg/m² load inertia to start. This results in 493 kilojoules stored in the flywheel, which is a lot, and clearly much more than we need for one 30-second move. But I'll start here and bring it down to a more optimal value. But before the kinetic buffer can function properly and manage power flow to the DC bus, a motor and drive must be selected first. Kinetic buffer sizing is an iterative process. There's no way around it. That said, the entire kinetic buffer solution can be sized in about 10 minutes, as will be done in this tutorial. At this point, choosing the motor is about motor speed and inertia mismatch. For speed, we want something above 3500 RPM. Where the motor does not need field weakening at 3000 RPM. And for inertia mismatch, we can start somewhere between 80 and 200 to 1, and then resize the motor and drive later as needed. Normally, such a high mismatch makes it difficult to control the load, but being a direct connected flywheel, this high of an inertia mismatch is controllable. So I'll set these filters and then choose this motor. Note, this motor's max current is 250 amps, so I want to choose an inverter that can provide at least this amount, which is what I have done. Again, I selected a motor that is not in field weakening mode at the 3000 RPM constant velocity, so it is not operating continuously at a lower efficiency, which would be wasteful since the motor will be running at the constant velocity speed all the time. Now I will open the power versus time chart to get a good view of all the power flow and energy storage in the power group. Note, we are in normal mode. The first plot to focus on is the system energy profile, which does not include the kinetic buffer energy. The kinetic buffer constant velocity energy is 496 kilojoules, which includes the motor inertia, which is why it is a little more than the value in the kinetic buffer form. So, we can reduce the kinetic buffer speed and/or inertia to something closer to the application requirements. Let's reduce the inertia to 5 kg/m² and see how that looks. With almost 250 kilojoules, we have plenty of energy in the flywheel for one 30-second move. Let's see how it looks in backup power mode. In backup power mode, we have two inputs, time of power loss and power loss duration. And let's deal with one 30-second move. The first 30 seconds is the normal sequence until the main supply fails, and then the kinetic buffer engages for the next 30-second duration. Looking at the performance, the kinetic buffer drops to as low as 1500 RPM, which is a good value with 500 RPM reserve. So we probably have the solution already. That said, I have some velocity room, so I'll reduce the flywheel inertia to 4 kg/m². And then we get a low of 931 RPM for the kinetic buffer. And this triggers a system check message. So I'll switch back to 5 kg/m², which is a good solution with adequate reserve. Now let's break it down. The kinetic buffer has almost 250 kilojoules stored and the application need is 123 kilojoules. Why the large difference? First, subtract the minimum velocity energy at 1000 RPM, which is 27 kilojoules, leaving around 220 kilojoules net. Then consider the energy required to decelerate the motor inertia. Then add the motor winding losses and the inverter losses. These three are about 20%, which gets us down from 220 times 0.8, which is equal to 176 kilojoules. What else is missing? Well, there's a 5 Nm thrust load for the flywheel. This is modeling friction, which is so important for something that runs continuously at speed. So, 5 Nm at 3000 RPM is 1.57 kilowatts, which is 47 kilojoules over 30 seconds. Therefore, 176 minus 47 is equal to 129 kilojoules, which is very close to the 123 kilojoules system energy value. And there you have all the pieces of the energy puzzle. Now, back to sizing. What if I need the power loss duration to be 3 by 30 second moves? First, I'll switch back to 10 kg/m². Then, I'll change the duration to 90 seconds and everything seems fine. Notice how the kinetic buffer energy declines with each 30-second move. These are the losses in the system, including thrust and friction in the flywheel, motor winding, and inverter losses. Also note the kinetic buffer velocity has dropped below the 1000 RPM minimum to 940 RPM. See the yellow shaded band showing the kinetic buffer is below its minimum velocity. It is also interesting to see the motor performance chart. With each 30-second move, the kinetic buffer velocity decreases, and then for each 30-second move, more torque is needed to get the same power to the DC bus. And if I change the load back to 5 kg/m², the kinetic buffer runs out of energy altogether at 65.7 seconds, shown by the red shaded area. And now as the kinetic buffer speed drops well below 1000 RPM, more torque is needed until the motor max torque is reached. The design requirement is for the kinetic buffer to power one 30-second move, and then we assume the machine stops. I will go to axis 1 and delete all moves after 60 seconds. And back to the power versus time form. And everything looks good. Notice the duration still is 90 seconds, but since the sequence ends at 60 seconds, the effective duration is 30 seconds, which I will now set for consistency. It is important to note that the sequence in backup power mode is separate from the normal mode sequence. In normal mode, there are 6 30-second moves, and in backup power mode, there are only 2 30-second moves. The kinetic buffer topic is explained in detail in the help file. To load the help page, go to the rotary mechanism form, select the kinetic buffer tab, and click the help button. It covers everything in this tutorial, including understanding the different voltage levels. This concludes the kinetic buffer tutorial. Thank you.